Welcome everybody. Welcome back to the Inikus project. So tonight we're gonna be taking a break from working on the lights a little bit. We've done a lot of work on them and they look great, but there's still the problem that the computer needs to be plugged into the lighting kit in order to run it. And we want to make that no longer a problem. So what we're going to do is attempt to add an SD card to the controller board. So our little controller board here, our Accelerate FPGA based Arduino is going to be used, and we have these little SD card readers. So we're going to add a micro SD card to it. And so I've got to get these things connected somehow and then start programming and see if I can get it to work. So that's going to be, all of that together is a massive step. There's a lot involved there. So we'll just start one thing at a time. Going on previous approaches, I'm doing less and less off stream and more on the actual stream. Sorry, I think my webcam's a little crooked here. There, that looks better. I'm doing more on stream, so that means I am planning things out less. So I'm going to start, well, not start anything really. Rather than look stuff up beforehand and learn how to do it and then just do it on stream so it looks like I know what I'm doing, I'm going to start researching stuff on stream as well. I'm approaching it more blind, and so that you can see kind of what it looks like when I don't know what I'm doing and I have to learn something very quickly and then apply it. So it's going to be a little tricky. I'll do the best I can. There's going to be slow points where it's just me reading things, or if you want to help out, and I'll tell you what I'm doing so you can look stuff up on your own if you want to try and help. And we'll just go from there. And you'll just see what happens as I grow my own knowledge base and then learn how to do something. So that being said, I guess we should jump into this. I don't think there's anything. I don't think we need the coding screen yet, but I'm going to pull it up. I created a new test project here. And so this is what we're going to be doing. Rather than messing with the actual project of the LED lighting kit, we're going to be just trying to literally write something to the SD card and read it. And that way we can test if that works and figure out how it works. And then we can add all that stuff into the existing project. So I'm going to update our goal real quick because I think that's important. Give me just a second. It runs slow. There we go. Connect the SD card reader to the Arduino. So literally connect the wires, because actually I don't even know how to do just that, so that becomes its own goal. And then let me adjust this so you can see it. There we go. All right, so we're going to connect the SD card reader to the Arduino. Supposedly that won't be too hard. We know that the SD card reader uses SPI. And we know that this thing has SPI support for it. What we don't know is where exactly that is, like what pins are used, and we don't know if we can get that working with the NeoPixels at the same time. So that's a whole series of steps, but we'll try and knock it out as easily as we can, or as fast as we can. And along the way, if you have questions or suggestions, as usual, ask me whatever, and I will try and answer as best I can. Or if you have an idea, let me know, because that could probably help save me a ton of time. All right, so we'll drop back here to this view. And then I am going to move some stuff out of the way. Well, actually, first things first, I really need to figure out how exactly to connect this. Let me see here. Actually, I'm going to go and pull this up. So this is the company that does this, and let me pull up my screen here. There we go. Okay. Wow, I almost use the same blue they do. SPI, Serial Peripheral Interface. It is 4 wires. The first wire is an enable line. If it's high voltage, it's usually something is disabled, and then if it's low voltage, it turns on some sort of peripheral. And to back up a little bit, this is a way of connecting a peripheral device to your main computer. So you have your enable line, you have your MOSI line, master out, slave in. So it sends data out from the master control board to the peripheral device. And then you have your MISO, master in, slave out, that sends data back from the slave into the master. And then finally you have a clock line, and that clock line controls the data rate. That's a really complicated way of just saying it's another type of serial communication interface. So other types of serial, there's I2C and then UART. UART is fairly common because you can actually run it over USB cords. And our lighting controller actually uses a form of UART that is running over the USB cord to the computer. So that's what SPI is. It's just another communication interface. It allows 2 chips to communicate with each other. So you could think of other communication interfaces too. How's it going, Beth? Other communication interfaces are like, HDMI. An HDMI cable is a way to communicate video and sound between 2 devices. It just sends data back and forth. USB-C, any form of USB, an optical cable, VGA, DVI, DisplayPort, all that stuff. These are all interfaces, and an SPI is just a very basic form of that because you're not sending a whole lot of data. That was probably a lot of explanation for something like that, but that's actually something I know a little bit about, so I like to talk about it. All right, so our product that we're looking at, is the Accelerate. I really hope they don't get annoyed that I'm showing their website on stream. All right, this thing right here, and then what we need, those are the places you can buy it from. We need like a pinout or something. They've got to have Accelerate docs. There we go. Let's do a user manual. That sounds like it'll help me out. I think I remember this being its own separate thing. Schematics and layout, that could be helpful. Connect to ground here. Here's how the ADC works. I2C UART SPI. Here it is. Interface should operate the same as if you had an internet board. The only alternative is that we've seen some SPI. Oh, these are just sampled by a shield. Okay, interesting. I didn't know about that pull down. Alright, and then finally schematic. There's a register summary. That's just a lot of... Oh, that's really dense. The registers are the way you control the different, external devices, so... Schematics and layout. There we go. Clock. All right, it's probably this first page. I apologize if this is a little hard to see. Their schematic is very faint. So there's the USB connection. I feel like I'm getting nowhere with this. Give me just a second. I could have sworn I've seen something about this before. About how to actually do it. I'm back on the same page again. I'm just searching through it for SPI. There's a pretty good chance, too, that this just isn't going to work because of some stuff that I just haven't been able to, or just haven't realized. But I'll learn as much as I can while doing this. Oh, here we go. Pin map. This would probably be useful. Aha! Okay. So if we look here, let me zoom in quite a bit. So here's our board, right? Matches what I have here. If I look down here, you can see, I mean, you can see various different things. 5 volt, 3.3 volts, grounds, voltage in, reset. If I go look at the other side, there's just a bunch of the different digital outputs. D0 through D13. I'm using D6 for the lights. And then down here, we can see the things I was talking about. SPI1 master in, slave out. SPI1 clock. SPI1 master out, slave in. So that kind of stuff. And then 3.3 volts. And then I think this thing is actually expecting 5 volts. So we'll have to wire it up so that it does that. And then as well as there's no select line here, so we're going to have to make one of our outputs here the select line. All right, cool. So let's get started on that then. I'll keep this diagram up. And then I'll connect everything to SPI1, because I think that's the one I most likely want. It's also important to note that in a lot of cases, you can, it doesn't seem so on here, but on some boards, you might have multiple things, like multiple connection points, be connected to the same thing. And so you have to make sure that anything that you're using doesn't conflict with anything else that you're using elsewhere. I don't see any examples here, so that's good. All right, so I'm going to keep this up, and then I'm actually going to go back to this other camera and then set up a soldering station, because we're going to have to actually connect everything. And then I'm going to tilt this camera down. I'm working on getting 2 cameras at some point, but for right now, this is what we're stuck with. So I'll get that out of the way. All right, so we have some things here. I also have a breadboard, some solder, and some jumper wires that we can use. And let's go ahead and get this thing heating up. And get our sponge wet without getting anything else wet. All right, and then I have to use this breadboard because of the way these connectors work, but that's okay. So now I just got to make sure to remember where everything is. So I'm assuming I'm going to use orange for power, black for ground, see, blue for master in, white for master out, and then let's see if we can find any other colors. I have yellow. Looks like that's the only other color I have, though, so I'm going to have to use double of one color. Yellow for the clock line. And then we'll use blue again for the chip select. Actually, we're going to use white, just to make sure they're both outputs. Keep everything from going weird electrically. Okay. That looks good. And then we gotta solder everything in here as best as we can. So let me break some of this off. I suspect that this part of the process, because of all the trial and error that's going to have to be done, and this kind of like communication level stuff does require a lot of trial and error, this might take a few streams. So be patient with me, if you don't mind. And we'll figure it out as we go. Trying to get this to about 750. There we go. And I will do the best I can to entertain as we go as well. But, you know. There's only so much I can do there. I think I really just need to solder the 3 major lines. The miso, the mosi, and the clock. Everything else can be kind of, can just be plugged in at different places. Also, something else to note, I don't know if everyone saw, but I have actually put up the first YouTube video on the main channel. So if you go down below and click on the YouTube thing, that'll take you there and you can watch that at some point. It's very rough, so please don't judge me too hard. I'm just learning how to use new software and everything. I'm using DaVinci Resolve, and I've never used that before, so it's taking me a little bit of time. But I'll start putting more and more up there. I'm gonna put up the Millennium Falcon build in each of its own separate parts, and then maybe like at the end of it do like a full, you know, long version of the time-lapse video. Do I have my little... I used to have a heat board around here. There it is. So I'm probably going to do that. I'm probably going to put up the Millennium Falcon in separate builds, but then after that, each project might be its own just singular video. Because I don't know that doing a video every time for a summary video for every time I stream is really that interesting or that useful. Alright, this is master out, slave in. Which goes over here to this one. Pin 3. As usual, I'm trying to do all this without burning myself. I think I've got a line on the next project we're going to work on too. Once we get this SD card added to this thing, I think we'll be pretty much done with this for now. All right, this yellow is the clock. Because I'll be ready to move on to another project. I hate to leave the Millennium Falcon because it's really cool, and a lot of people seem to like it, but there's other stuff we got to work on. I'm trying to get to the point to where we're making products based on people's requests, and I'm starting to actually get some requests for projects. And so I don't want to like take too long to get there. Also, if you have a good idea for a project, please let me know. I got a request recently for a remote controlled snowblower with a flamethrower on it. And I had to turn that down because I don't, not because I don't think it'd be cool, but I don't have the money for a snowblower and flamethrower. But maybe we can put that on the backlog and do it one day. Alright, so now I need to figure out where to plug in all this stuff. I'm done using the soldering iron. So I'll unplug this and get it out of the way. Alright. right. Now we got to figure out where all the rest of these wires go in. So I'm going to pop back to this. You can kind of see what I'm looking at. So we have our reference here. And then I have all my wires here. So I know that this black wire is ground. So we need to find a ground. And as you can see, there's a couple right here that we can make use of. So I'll plug it in there. And actually, I've just realized now, too, on the board, you may not be able to see it, but it's actually labeled what everything is. The only thing that wasn't labeled was those SPI lines, which makes that annoying. All right, this is power, which I believe I need 5 volts. And then finally, this line. Actually, you know what? I need a longer wire for this. Here we go. This is our enable line. It needs to be set low for the chips to start talking. So we will put that into a random, how about 13? I believe 13 is also the LED on the board, so we'll see it light up whenever it activates, which will help me debug it a little bit. Prove that it's working. Okay. That's good. That's all connected. Let me pull up something else real quick. Sorry. I need to eject this. There we go. All right. Got an SD card right here that I can plug into there. And so the plan is to try and write something to it. I have no idea how SPI in Arduino works, especially connected to a memory card. So that's a total guess. I'm actually not even going to plug that in yet. All right, and we'll move some of our soldering stuff out of the way here. And then I'm going to go back to this, because now we're going to be writing code. And I'll hold things up as I think they become interesting. All right, move that off to the side, and then we'll go back here. Okay, so we've connected the SD card to the Arduino. So now we need to update our current goal. So the next thing would be, let's see, properties, there we go. All right. Let's, I guess, start SPI communication. So go through and configure everything. The SD card. There we go. All right, that's what we'll do for now. Looking good. And I'll zoom in a little more here. I meant to get a dark mode for this. I apologize for not doing that yet. All right, first things first, I'm going to plug it into the computer here and see if it explodes. All right, nothing went horribly wrong. That's a good start. All right, and then I can't remember. I'm just looking up an example how to do a pin output. I don't usually do, I know a bit of me, I need dark mode. By the way, since I have you on here, you have asked me about a possible project for you, and I would like to, I'm trying to get this part of this project done so that I can get to that. So if at some point you could submit a formal project request for the thing you were asking me about, I would like to start reviewing it and get a plan together. Because I think I could use one of those too. So, and for those of you that don't know what you're talking about, I will let you know as soon as I get a project request. Okay, pin mode. Okay, pretty straightforward. So if I go here, just do pin mode, and then our pin is 13, I believe. Yep. And we want this to be output. And then here, we can literally copy something to see that it works, but digital write. Also, I apologize once again if you can hear my upstairs neighbors. Sounds like one of them is doing their best impression of a bowling ball right now. And then we want to delay 1,000 milliseconds. And then we want to set pin 13 low. And then delay another 1,000 milliseconds. Okay, so the point of this, let me pull up, there we go. This so you can see. So basically it's going to blink a little LED on this board. And that's just to show that that control line is working, because that control line needs to be made forced to low in order to activate the SD card. So basically you can power the SD card and everything, but that control line functions more or less as the actual on-off switch. If it's high, then the SD card is going to just ignore everything. Nothing's going to happen. And then when it goes low, the SD card has a trigger in there that when that line goes low, it knows to turn on, boot up, and start listening for requests. Whether those requests be read, write, or create files, anything. So let me compile this. This should compile on the first try. Hey, it did. That would have been really embarrassing if it didn't. Okay, so now I'm going to run it, upload it to our little board here, and then we should see the light blink. There it is. All right, so I don't know if you can see it, but you're looking at the blue light there. It's blinking on and off. So that means that our code here is working correctly. As we know with Arduino, the way they set this up is a little weird. They have a setup, rather than a main function, they have a setup function and a loop function. Setup runs once at the beginning of the program. It's the first thing that runs, and it's where you put all your setup stuff. So I had to set the pin mode to pin 13 as output. Pin 13 can also be input, to where it can read data coming in. It can read if the voltage is high or low. But in this case, I set it to output, so I'm forcing the voltage high or low. And then also, Deja Taki, thank you for the follow. Glad to have you here. If you have any questions or suggestions, please let me know. All right, so then after the setup runs once, our loop function runs repeatedly. So that's why the light kept turning on and off. Even though we only had it turn on and then off, it keeps repeating this loop over and over again. So we flash it on and off a bunch. Okay. So that looks good. Next thing's next. Wow, we're going through a lot of difficult concepts tonight. Not difficult, but just a lot of concepts really fast for this sort of thing. This particular board is not actually an Arduino. It is an FPGA. It is an FPGA that is programmed to look like an Arduino. So we have to figure out, and actually, I don't know if I need everything. What are the limitations of an Arduino? It really depends. Fun fact, Arduino is more like a brand. When we say Arduino, typically we're referring to an Arduino Uno, which looks like this. It's this shape, but it's Arduino is actually, there's several. There's Arduino like Megas and Arduino Minis and Arduino Circulars, and you can buy them in all kinds of different things. And I'll actually pull up one here. I don't think I have a... Okay, so I only have a couple. Arduino AVI. Okay, so here we go. Here we go. I'm pulling it. So you can see, like, there's just a ton. Uno is the most common. But then there's Nano, Mega, Mega 80K, Leonardo. And these are all just, they have different things, different capabilities on them. This particular one, the Arduino Uno, we can actually see some of its limitations down here. Where my sketch used 924 bytes of memory out of 32,256 bytes. There's 32 kilobytes of memory for program space, okay? Now think that to your computer where you have a hard drive that's 2 terabytes. All right, 32 kilobytes is tiny. You're not going to be running GTA 5 on it anytime soon. And then if you look here, my dynamic memory, that's the RAM. Out of 2,039 bytes total, some of that is used up for other things, so it's actually 2048, which you can see here, maximum of 2048. I have 2 kilobytes of RAM, 2,048 bytes of RAM, and that's all I have. So once again, not going to be running Grand Theft Auto or, you know, Final Cut or streaming on Twitch on it or anything. It's a little computer with just 32 kilobytes of hard drive space and 2 kilobytes of RAM. Also, the speed of the processor is 16 megahertz. That's compared to processors today that run in the gigahertz range. So, you know, most video games require you to have a processor of speed greater than 3 gigahertz and multiple cores. This has a single core that runs at 16 megahertz. So, you know, almost 1,000 times slower. So those are the kind of limitations we think about. That's why it does very basic tasks like this of sending data, receiving data in one line and sending it out the other. You know, common uses of devices of this size are things like TV remotes, car keys, appliances, things where like there's not a fancy display, there's just a few buttons and it's controlling a few basic functions. Printers have a lot of controllers like this in them. Now, FPGAs are on a whole different level. You can actually, most Arduinos have things like, have a microcontroller on them, which is its own kind of self-contained computer, and everything is hard set. It's a computer that does specific things. An FPGA is a chip that you actually program with circuits. It literally has a computer programmed into it. It's kind of like the same thing as those people that make computers in like Minecraft. They go through and use redstone and, you know, make a computer, a functioning computer. Somebody did that on this FPGA. They literally wrote out all of the computer's functions in code. And then, so I can program that on there and then write some software to go on top of it. Could you make some sort of arcade cabinet with one? Absolutely. The only tricky part is the display. Like, so, I mean, if you're just talking about the arcade cabinet, like buttons and lights and things, yes, 100%, that is straightforward. You could buy something off the shelf for $20 that could run all the lights and buttons. You'd have to interface it with a game is more complicated. If you wanted the microcontroller to run the game, you would need a pretty powerful one, pretty expensive one. But if you were just interfacing with a computer to have the controls, then yeah, you could absolutely run an arcade cabinet with it. All right, so we need to figure out how the SPI works in Arduino, and then we need to figure out how to use SPI to communicate with an SD card, because that's a whole nother thing, the way SD cards work. So I have this off screen over here. I'm just Googling info. If you know anything about Arduinos, how they work, like how SPI works, that'd be great to let me know. But otherwise, we're just going to have to figure this out as we go. Arduino SPI SD card example. And then I'll try and pull things on screen here as I'm showing it. As long as I verify that it's something that I think I can show. Okay, here we go. This is from the actual Arduino website. So SD card library allows for reading and writing to SD cards. Library supports the FAT16 or FAT32 file systems on standard SD cards. This is just a way of storing data on the SD card, the FAT16 or the FAT32. Typically, you wouldn't even think to look into how those really work, because most of the time, like, that's just not something you think about. All right, to use this library, include spi.h and include sd.h. Examples, card info, data logger, dump file, So data logger would be cool. You could record a bunch of inputs and then constantly store that data to an SD card. If you wanted to put an Arduino, attach it to a scientific instrument like a pressure sensor or, a light sensor and put it out somewhere, you wanted to see what the pressure of the atmosphere was over the course of a week, you could plug it in and set it up to log data to an SD card and just make a big file that has pressure over time. So Arduinos are great for little scientific instruments like that. Then read write. This is the one we probably need because we want to read and write to it exactly. You need an Arduino board, Ethernet shield, or a board with an SD card slot, and a formatted SD card. I don't know how well this is going to work. There's a lot that I'm just trying to learn on the fly here. All right, so code. Oh, wow. It might make me use other pins. But it's using SPI, so I would think that if I attach it to the existing SPI bus, I should be fine. While we're figuring this out, since everybody's on here right now, let me know how your Thursday's going. If there's any interesting stories, because this is going to be boring for a little while. So if anybody has anything they want to throw into the chat right now to shake it up, that'd be awesome. While I sit here and nerd snipe myself into trying to figure out what the heck is going on. I don't think it's as simple as just calling sd.open. And the reason for that is if I had a normal Arduino, it probably would be that simple, but I don't have a normal Arduino. Hold on. Oh, this is interesting. All right, I found a thing on GitHub that looked like somebody's project for figuring this out. But I don't think it's everything I need. Well, let's try it and see what happens. I'm going to use this example code and see what happens here. All right, I'm going to pull that off to the side. And use it as reference. Okay. So pin 13. All right, so we need to define a couple things just to get us started here. Let's see, SPI, yes. I'm already doing Python again. I need to not do that. Define SPI, CS. CS is our enable line. Chip select. So one of the cool things about SPI is you can connect a lot of the bus lines together with different chips. So you could have a bunch of them on a network. As long as you run a different chip select line to each one and just turn on one at a time, you can communicate with a lot of devices on the same bus. And all the ones that are turned off will just ignore it. And then the one that's turned on will respond. So that's a way that why SPI is actually really useful on circuit boards is you can connect a lot of different chips together with just like 4 or 5 lines. SPI CS pin, and we'll set that to 13. Okay, and then we'll substitute that in here. And honestly, we don't ever want to stop communicating. So we're just going to start off by setting this line low. And then we're going to ignore the rest of this. All right, then looking at my example here, I need a few libraries. So include. And then we need the SPI library. And we need the SD library. All right, excellent. Now, oh, fun, we get to create file objects and everything. I'm literally just copying it almost verbatim here, and I don't want to do that. Let's call it test file. You know when you copy your friend's homework and change it just a little bit? Yeah. All right, and then also we want to open the serial port. So what I think I'll do is I'll put a little text file on this SD card, and then I'll try and read what's on there, and print it to the serial port. That would be probably the best test, and then maybe do another function where I write to it. All right, so serial.begin. All right, as we talked about before, serial communication on this device is 115,000 baud, 115,200. That's just a random standard number. All right, and then I didn't realize you could do this. They recommend waiting for the serial port to connect. That's really interesting. I didn't even know you could do that. Is it a Kellogg's or General Mills cereal? I'm trying to decide if I should ban him or not. The temptation's there, but I'm going to resist. You got lucky, Atikta. All right. I like that it doesn't... Oh, that's not a comment. That's why I did that. I still have Python on the brain. I'm keep trying to type things in a Python way. Okay. Set up SD card. So we're going to do the thing where we fragment our memory. I know who it was. I just... Oh my goodness. Y'all are ridiculous. I'll just say initializing. I don't want to use too long of a string and fragment the memory like I did last time. That'd be terrible. Also, did anybody watch the Mars rover landing today? That was cool. Can we talk about how a rocket-powered sky crane was the best way to put that rover on Mars? And why that isn't something we use in construction right now? All right. Okay. I'm just learning there's functions here. Serial.begin, and they give an argument of 4 as a parameter. Why is that a thing? Or SD.begin. Oh, you named the pin. Oh, wow, that's interesting. All right, this is probably going to take a few tries. Yeah, it was cool stuff. It's what NASA calls the 7 minutes of terror. There's 7 minutes where they just don't know what's going on and if it's working. And because it's on Mars, the speed of light delay is such that in order to receive something and send data back, it's like 20 to 40 minutes. So you can't control it. It has to do it all on its own because if you were to send it a signal saying, start landing or something, it's going to take 20 minutes to get there, because that's how long it takes light to get to Mars from Earth. And you physically cannot send something faster than that. So it's all remote, it's all automated. And it literally pops out with a crane. The crane fires up some rockets so that it hovers, and then the crane lowers the rover down onto Mars, and then detaches the cables and flies away, and then crashes somewhere away from the rover so it doesn't damage it. The crane doesn't usually survive the mission. The crane never survives the mission. It was 11 minutes today? Okay, yeah, it varies depending on where in the orbits we are around the sun. Anywhere from 10 to 20 minutes, but yeah. That was wild. And they were successful. JPL knocked it out of the park. It was awesome. 7 years of engineering and then 7 months of time. Once they launched it last July on a rocket, and it took 7 months to get there, which is why it didn't happen till today. Because Mars is so far away. 1.1 AU. Okay, that makes sense. And an AU is 8 minutes, the speed of light. So, okay. I have no idea if this is going to work. All right, so we're setting up the SD card. And then, so evidently, we just tell it what our... Okay, so what this is saying is when we do... Here, let's do this. So I'll show you what I'm talking about. Start communication. And then what it's recommending is this. If not, sd.begin. And then the argument you provide here is actually the chip select pin. So it handles that on its own. And then this returns true or false depending on whether or not the initialization worked. Okay, so I guess that's a good way to tell if something failed. We should just start with this. So serial dot print failed. It's gonna say failed because I have no idea what I'm doing, and I know this can't. Do you have to format the card? Yes, but it's already formatted. Or it should be. I plugged it into my computer before this and erased everything, so. Seeded. All right. And that deserves 3 exclamation points because it'll be an even bigger deal. And then I need to add new lines to all of these. And then here in our main, delay 1,000, and then serial.print waiting. Just to show that it's still running. Okay. Well, everything compiled. Wow, adding those, so let me make sure I'm showing you all this correct thing. If you look down here at the bottom, Sketch uses 8 kilobytes versus before it was using less than a kilobyte. So adding this SD card and this SPI interface library increased our program size like 8 times. So that's really funny. All right, so I'm going to take the SD card here and plug it into our little SD card reader. And then this just, there's so many variables here, so there's no way this works Does it care about the file format type? Probably, and I'm sure I'll figure that out in just a second. Okay. Let's upload. Just get the disappointment out of the way. I'm sorry I'm being a little bit of a downer here. It's just SD cards are very finicky when it comes to these type of devices, and they almost never work on the first try. I've never had a good experience trying to get an SD card to work on a microcontroller. So, you know. Yep, it failed. And then it printed succeeded anyway. I forgot to put a hold there. All right, so let's go back here. And just, if it fails, just kill the program. Infinite loop. You know what, this is going to be really hard to debug, and I might have to take this somewhere and do it somewhere else, because I don't have a logic analyzer or an oscilloscope or something, so I can't actually see what's, if anything, is happening on the lines. All right. I think that uploaded. Let's try it again. Okay, yep, definitely failed. But we don't know why. I wonder if there's if I can check here real quick. This is, so recently I was talking about getting a different microcontroller that already, like an evaluation board that already had an SD card slot on it. Then I could get out of Arduino anyway. You know, I have enough time between Tuesday's stream. I might do that anyway. And just completely scrap this and go to that, because that would honestly be way easier, I think. Yeah, that might be an option. Because this Accelerate board is so cool, but it's just so complicated to use, and I needed to move away from it anyway. And I need to pick a different controller for some of the other projects I wanted to start working on. So that's probably a pretty good option. We'll learn as much as we can for this stream, but maybe we'll pick something else for next time. Or if I can't figure this out in the next 15 minutes about, like, even, because, like, I have no idea what I'm doing wrong here, because this is such a foreign piece of hardware and everything. I might actually just start looking for a board here on stream, something that I could use. Probably use an AVR board of some sort, just so we can use Atmel Studio and get that started. Okay, so I'm going to pull up this right here. This is our SD card library. Yeah, save a lot of development effort. Absolutely. I have enough experience with Atmel Studio. I can more or less figure a lot of things out. And the important thing with Atmel Studio versus Arduino is that it has a debugger, which, you know, I'm impressed that in this day and age, Arduino still doesn't have that. But I guess the way the hardware abstraction, the way that works, that would be really hard to do. So, all right. SD class, let's see here. Let's look at our begin function. This begins use the SPI bus, digital pins 11, 12, and 13 on most Arduino boards, 50, 51, 52 on the Mega, and the chip select pin, which defaults to the hardware pin. Boards, note that even if you use a different select, the hardware must be kept as an output, or the SD library functions will not work. That's interesting. Bus, true on success, false on failure. But it doesn't give anything else. There's no indication of what exactly failed. Like, it could be communicating perfectly and I just don't have the SD card formatted correctly. Or it could be a bad connection. I don't have a way to debug all of that. If you want to offer a donation, I will apply it towards my oscilloscope fund. sorry. All right, let's go back and see what some of these other functions are. What does exist? Test whether our file or directory exists in the SD card. Make directory. This makes a file. Makes a folder. Open should open a file. It will be created if it doesn't exist. Remove deletes a file. Yep, delete a file. And then remove directory deletes a folder. So everything you need here to get started. And then in the file class, they have all the functions you would need to read and write from files. Okay. Let's see. Just seeing if I can find something. I'm curious if I should just try connecting the SD card to the pins it was telling me to. That it says it uses by default, 11, 12, and 13. That's probably one more thing I could possibly try here. That wouldn't be too hard. I also don't know if this library supports like a max file size. I have 128 gig card, or a max like card size. Sometimes they do. Yeah, there's not really a lot on. So yeah, that's why I'm thinking I need to move to a different. Yeah, cspin is an optional parameter. Yeah, I know it is. It's the default. I don't even know what the default is on this board. It doesn't say. It says the hardware select pin, but I don't. It doesn't actually tell me in the user manual here. Here, I'll let you see this. Which pin that is. SCL, SDA. Wow, they have an I2C interface? That's cool. Actually, let me look at something else here. Maybe I'm doing this wrong. If I go here to tools, what's their names? Alorium has a lot of libraries. So maybe that's what I'm doing wrong. Ah, here we go. Accelerate SPI. That's probably what I need to be looking at. The question, so you notice there's an SD up here, but that's for the, what's that called? The hinge? H-I-N-J? I don't know how to pronounce that. That's a different board than the one I have here. I have the accelerate. Well, okay, I guess they all say accelerate. I have the base accelerate base model. So that's interesting that accelerate GPIO is an option and digital IO is an option. And I am actually just using the Arduino commands and it's working just fine. But I probably need to use this. The problem is I still don't have a way, like, I still don't understand how SPI protocol works, like for SD cards. All right, that's something that's worth Googling. Arduino reference. Adapted from Arduino's. Functions. Okay, but I need to see an example of it. Hello, I am new from Kentucky. From Kentucky, really? You cold right now? Just asking. Well, welcome to the string, Eldon. We're learning how to use a really weird Arduino right now. And I am trying to figure it out. Weird. I've seen where they support it, but I don't see an example. Okay. I think I found the source on GitHub, maybe. Oh, this is interesting. It's a library that might work. Clicking through this GitHub right now just to see what I can figure out. All right, let's see. I guess that's the least helpful README I've ever seen. What's this file say? Nothing. What is snowshoe? Is that a different board? Oh, it is. It's okay. So this is not even for this board. All right. Yeah, this is going to end up being very complicated. So I think what we're going to do right now is pick out a different evaluation board. All right, got a couple things pulled up here. I just got a notification for breaking news. The Mars Perseverance rover sticks landing. That's old news. I think I've used this one before. I like this board. Sammy 70. Let me see. Here we go. Looks like... Oh, no, wait. That's not what I want. Here we go. Let's find this on DigiKey real quick. It's a Sammy 70 board. Sammy 70 explained. Does it have? It has an Ethernet cable slot. If we want to control our Falcon over Ethernet, that'd be kind of cool. Control it over the network. Explained guide. Let's look at this. One 4-bit SD card connector. 4-bit. That's probably a high-speed multimedia card interface. An HSMCI, I think is what that is. So it's not even SPI. So it'd be really fast. This would be a pretty fast board too. It runs at what does it run at? It's an ARM core, so pretty robust. Sammy 70Q21. This is an option. How expensive was it? $40. All right, not terrible. It seems like a lot. This, I mean, look at it. It's a 144 pin micro. It's got all this I/O on it. And then it says it has an SD card slot. Does it actually? Oh, it does. It says it right here. SD card slot, bottom side. Okay. I know this is probably hard to see because I'm not zoomed in very far. But it's there. It's on the underside of it. It doesn't say it's a micro, so I'm assuming it's probably a full size. It's a really cool board, but it's a lot. It's expensive and it's has a ton of I/O. It'd be overkill for everything. I don't know if it would fit in the Falcon, actually. That could be a problem. All right, let's look at... let's just go back to embedded evaluation boards, and then... we probably want active, in stock, so that'll give us everything current. DigiKey is a great place, by the way, if you're just looking for... trying to narrow down parameters to find something. Alright, operating system. We don't need an operating system. How about Windows 7 embedded? Fortunately, they don't give me a lot of options for filtering here. I would love to filter on the features. Alright, well then I guess I could just go through here and... I said I wanted something AVR, right? Something ARM. Atmel ARM. Adafruit. You know, I don't see any Atmel microchip. Here we go. Microchip bought Atmel recently, I believe. Yep, Atmega. Well, that's a lot of stuff. With no connectors on it. Alright, I need something with an SD card slot. Sam D21 Explain Pro. It's kind of expensive. Here's the Sammy 70 again. That has an SD card slot. It looks a little smaller. The Sammy 54 Explain Pro. Is it cheaper? $75. Why is it 75 bucks? Wow. Sam 4E, $102 for this. Oh, that looks like RAM on it. That's probably like for like an operating system. Could use a PIC micro. That's an option. I've never used a PIC micro before. Sam V71. Wow, that's a lot too. That's actually got the header. You can see on there, it's got the headers on it for to put an Arduino on top. Wow, so Atmel has some expensive boards. If you want anything more than basic. Explain nano. Oh, shoot. What if we... No, I don't know if this would work either. I remember seeing this as a thing. Here, let me look this up. I know this is probably pretty boring because I'm going through this so fast and don't have time to explain what I'm talking about, but this is a cool platform. I don't think it has an SD card on it, though. Yeah, it doesn't, but I know that a version of their product does. 3.2. Here it is, the 3.6. Runs at 180 megahertz, Cortex M4, so that's pretty fast. 125 kilobytes of flash, 256 kilobytes of RAM, 4 kilobytes of EEPROM. That's pretty great. So plenty of power. So then it's got SD card support as well. This is a pretty common thing. The only thing I'd be worried about is the difficulty in running NeoPixels from it. That part is really hard. Because so this thing is programmed by Arduino. It's a Freescale processor. I don't even know what you'd program that in. So, and as we discovered previously, Arduino environment's not great for debugging. And it wouldn't be great, unfortunately, to run the NeoPixel interface. Let's see, to run the NeoPixel interface, I'd have to make my own delay function. And it's hard to, a custom delay function to delay on the nanosecond scale. And that's hard to do in Arduino. Let's organize this by price again. Whoops, wrong way. $787 for a kit. Wow. Oh, wow, that looks epic. All right, other way. Okay, so I was only looking at one page. They have a few things here. Let's see if we can find something that has what we need. Titanium Nano. It's going to have to, I'm pretty sure it's going to have to be an ARM core. It's going to have to be something fast. All of these are tiny little slow micros. In order to, my existing Arduino has a block built into it that can run the NeoPixels, run the high-speed communication that the NeoPixels require. These don't. So in order to run that high-speed communication, I need a very fast processor. Fast in terms of microcontroller. Cortex M0, that's probably too slow. We can check this one out though. The links are all broken, so I gotta go look it up manually. But just looking at that here, it's not what I need. All right. Let's keep scrolling through. Worst case scenario, I just pick that overkill board, spend the 40 bucks or whatever, and just do that. I really don't want to, but it would allow me to do a lot of other cool projects with it. Alternatively, I have to get my own. The heck does that have on it? Internet of Things. It's got a Wi-Fi chip on it or something. That's cool. That looks like it has a touch sensor on it. You can see in the side on the right side over there. I don't want to have to buy a $40 board for every little thing. I guess I wouldn't have to though. This is just a special case where I need something with a lot of power. Nope. I tried to do the 3D view. See if there was an SD card slot on it. But they didn't bother to show a picture of the bottom. Okay. Interesting. Hmm. And that's back to that one. They have a lot in stock too, which means they sell a lot. That might be worth it then. Just for this project, and then going forward, pick something a little less powered. I don't want to have to spend 40 bucks. It's on Amazon for $45. All right, maybe I'll order it from DigiKey then. That's the easiest solution I can think of, unless anybody can come up with something else off the top of your head. Because there's just no way to get a board that can control the NeoPixels fast enough, that can run the NeoPixels. Or I have to come up with a... I have to tinker around with this a little bit and figure out how the SPI works. I'm not a big fan of either of these options. There's no like easy solution. Hold on. Board SD card. I'll just search some specific terms here. Hmm. Let's see. Oh, interesting. So an STM part, which supposedly can support a micro SD card. I'm guessing that's what this is right here. Some sort of memory card slot. Oh no, wait, it's right here. Wow, this is a lot of a lot of board. USB there. Looks like USB there. I'm gonna guess this is super expensive. STM32 parts are actually pretty good sometimes. Let's see what we can come up with here. Yep, I accept. Hang on, gotta reload every time. Because why not? You know when they won't tell you the price, that they're usually pretty expensive. Memory card, yes. Okay, that's what we want. And then we're probably gonna want microcontroller unit. Can we select the core? Don't know if it'll let us. It also doesn't show pictures, which is kind of annoying, but that's okay. Display type. Wow, some of these have displays. That's crazy. Touch, crypto, debug connectors. Whatever we pick needs to be programmable through a USB cable as well. NFC on this one. What does this look like? Wow, it's got a screen and all that. SD card slot. It has a headphone jack just in case you want to do that. Oh, it's integrated on circuit. Okay, so this ST-Link is the thing that you use to program it, but if it's integrated, then it's good to go. So that's cool. So there's a few options. I mean, what is the cost of something like this, though? Available for order. At some point, it's got to give me a price. $250. Kind of expensive. This looks like the cheapest one, and it's probably pretty expensive. $200. Yep. Oh, man. I hate everything about this. It's overwhelming to try and figure out because there's so much that I don't know, but that's okay. Well, any suggestions? I think I've thoroughly bored my viewers. I went from 7 viewers to 1, so I apologize. Whoever you are that stuck around, I really appreciate it. Wonder. It's leading me back to thinking that maybe this is the best option. I just got to try and figure it out. But I'm not sure how to do that yet. All right. I'll probably cut tonight's stream a little short, just because there's not much going on and not much interaction. So there's not a lot to do. I'll try and debug some maybe over the weekend and see what I can figure out. Maybe I can figure out how to make this thing work, and then we can continue on next time. All right, then. Well, in stock and $30. Oh, you're looking at this right here? Yeah. I just don't know if this is fast enough to run the NeoPixels. The NeoPixels run it at 800 kilohertz kind of baud, and you have to have timing right down like to within like 20 nanoseconds or so. So there's not a lot of variation, and I don't know that this processor can do that. What is this? It's the MK6FX 1M0BMD18. Whatever Freescale part that is. 180 megahertz, so that's cool. So that might be fast enough. Might be. The thing is, the way I have to make a delay loop on this is to a custom delay loop is I basically have to do a loop of no ops, and at 180 megahertz I may still not get the resolution I need. You can figure it probably runs at half that for the device speed, so you could probably execute a no op every at 90 megahertz. So what is that? Again, I guess it would be 1 divided by 90 million. My calculator's not going to do that here. Oh, it's the programming calculator. Sorry. And divided by... What does that get us down to? 1 to the negative 8th. 1, 2, and 6. So that's a resolution of like 10 nanoseconds, theoretically. WS2012B protocol. At Arrow. Fine, whatever. really not giving good pictures here, are they? Just some screenshots from an oscilloscope. Hold on, I'm pretty sure I saw a better article. Oh yeah, it might have been this Adafruit one. Restored on Adafruit. Nope. Here it is. Okay. So this is how the protocol works, right? A 0 is a short time high and a long time low versus a 1, which is a long time high and a short time low, and then a reset is a long, long low. We have to get our resolution, it looks like in all cases, within 150 nanoseconds. If we look at this. So that's doable, actually. I think I could make that work. And because it's a teensy, it's programmed in the Arduino environment, I can port a lot of the code over that I've already written. Terrence, you may be right. This may be the ideal option, is to get a teensy 3.6 and then do it this way. Alternatively, do we do the teensy 4? What's this 4.1? I'm not seeing this. Oh, they have a 4.1 with a... It's a little bit cheaper. Okay. No. This, I think, is what we need to do. The 4.1 here. What is this? MIM. I'm going to... Because I heard about these, and this is insane. T1062. So it should be an NXP part, because it's free scale. Yeah, here we go. Product information. Okay, check this out. So this is the core that this teensy 3.1 or 4.1 uses, and check this out. Max operating frequency, 600 megahertz on a microcontroller. 600 megahertz. That's insane. Not only that, this board is actually a little cheaper than that 3.6, and it has the SD card reader. So this is the one right here. That would do it. We can't debug, which is a downside. But man, we can run everything, and we have a lot of power to do it. And if we look also, we get a whole megabyte of RAM. How much flash does it have? I'm sure it's configurable. I don't know that I have the exact one. The DVJ6A. DVL6A. Where's the J6A? Yeah, no, it's almost 4 times together. Yeah, it's insanely fast, and that's actually way faster than that Atmel board I was looking at. So it's almost twice as fast as that, or it is twice as fast because that was 300 megahertz. Hold on, let's see if I can find the... Alright, search the DVJ6A. Here we go, product information. Alright, 600 megahertz. Yeah, there's that. Where is the... I mean, I'm sure the memory is huge, but where is it? It's got a CAN interface, got some I2Cs. I'm sure it's got SPI on it. Something like this would have just about everything. It's an ARM Cortex M7. That's like top of the line ARM core. M7, does it really? 8 megabytes. Holy crap. Where did you see that at? I totally missed it. Is it up here at the top? Did I just totally miss that? Huh, either way. I love the Epic package too, 196 pin BGA package. You would not want to solder one of those on by hand, let me tell you. Okay, well, this looks like the thing that I need to get. I wonder if I can find it on like Amazon or something. Adafruit, Teensy 4.1 without pins. From the PJRC store. 2983. Free delivery Thursday, February 25th. Okay, a week from today. That could be acceptable. It was on the board description. Oh, there it is. Anyways, they're talking about SPI, I2C. I wonder if... Hold on, let me look at the data sheet. Sometimes, newer stuff sometimes has this 2812 interface on it, which would be epic. I don't think this particular one will. Nope. That's unfortunate, but that's okay. We can basically bit bang it. So the last thing we need to know is Arduino no op. How do we do that? All right, Arduino forum on very short delays. I guess you could just do increments. Okay, yeah, Arduino has, so you say assembly and then specify no op. Okay, so that's how you do that in Arduino. So basically, to make our loop, what we're gonna do is just create a function that runs a for loop where we can specify the bound, and then we'll just do no ops. And there will be a little bit of baggage on the outside of that because it has to increment a variable every time and all that stuff. But as fast as this processor is running, we should be able to get a pretty accurate kind of delay going. And then we can just, use that. And actually, I might be able to cycle the NeoPixels faster than I am now. It'll take some tinkering to get right. I'll need to get my hands on a logic analyzer or a scope or something just to see like how long it's taking. Because I don't know what the overhead's going to be, but I think that can make that work. All right, excellent. That's a plan. And that's what we'll do to get this working. And then I actually really like this platform. Even though it's Arduino, even though I can't debug, I can tolerate it for the fact that it's got so much power in all these interfaces. Can you use interrupts? That's a good question. I guess I'm sitting here thinking through about polling and everything, but if it's got timers on board and it has interrupts, then that would be the ideal way to do that, right? Does it have any timers? Teensy 4.1 timers. Interval timer supported on only 32-bit boards. Up to 4 interval timer objects may be activated simultaneously. Teensy only has 2. Interval timer. Set the interrupt priority level, controlling which other interrupts in this time is allowed. Or update. And okay, so it exists, but you can only use microseconds, and that's not a fine enough resolution. Because we need down to the at around 10 nanoseconds resolution. So we'd have to do it manually. We'd have to go down and figure out the registers and make our own timer setup. This is in the past why I've had to do it as that weird kind of delay loop, is just because a lot of the library functions just didn't allow nanosecond level timing. Interesting. Okay. Interrupts on Teensy with C language. I don't know how useful this is going to be. You said there was timers on this thing, right? Where does it tell me that? It's got quad SPI, that's cool. I don't know exactly where it was. It's got to have them. It's got a real-time clock. Here we go. FlexIO is highly configurable peripheral, sort of build your own collection of shift registers, timers, logic, and state machines. FlexIO can implement UARTs, I2C SPI, I2S audio, unique builds such as WS2811 library. Whoa. Hold on. What is this? FlexIO. It's got an Ethernet socket on it too. You can control Ethernet. Oh man, this is unfortunate. I have WS2812, not WS2811. What is this FlexIO? I've not heard of that. Programmable FlexIO. Is it a Freescale thing? Introduction to the FlexIO module. So, flexible input-output peripheral, highly configurable range, emulation of a variety of command protocols. 4 main components: shifter, timer, and pin. Exact hardware peripheral module. It's almost like it's a programmable module, kind of like an FPGA. If anybody watching right now understands what NXP's FlexIO exactly is, I would love to know. Register. 8-bit PWM mode. Applications, timers, 2 shifters, 4 pins. I wouldn't even know how to begin with how to program it, but I bet if you could do 2811, I bet they're programming it using, well, they're programming using something, but I don't. Callback function implemented. That's kind of cool. It looks like it has some built-in stuff. Maybe somebody's done this. Not it. Yeah, I know. This is. I've not heard of it either. WS2812. Non-blocking WS2812 LED library. It's compromise WS2812. It's fast. He doesn't. This is okay. Okay, I love how this guy did this. I'm looking at the. So he used a serial port and ran it at 4 megahertz, which is 5 times the signal required. And then just sent data through the serial port, even though it thought it was sending like UART. Basically, he ran it in such a way that it ran the NeoPixels. That's hilarious. He emulated that WS2812 communication interface using a UART. And he did it with a slower chip than the one I'm using now. That's a teensy 3 of some sort, I believe. All right, well, it means that I have options. Hold on, let's go here. FlexIO 2812. Hacker.io. I've got to be careful going to these random websites while I'm streaming. I'm just clicking on links. All right. Let's go back here. Yeah, you can always buy an adapter. Or you could do one of these ridiculous libraries that look awesome. Okay. Well, I'm going to probably wrap it up here. I think I'm going to get one of these to do this project. It would make it way easier, and it's smaller and offers a lot more flexibility. And then I think, oh shoot, you know what I didn't think about? I think these teensies are not 5-volt systems. I think they're 3.3 volt. Yeah, that would have to be because they have a lot of stuff direct to the chip. And that's not a 5-volt chip. How can we fix that? I guess I need some sort of voltage divider or something. I need a logic shifter, a level shifter in circuit to make that work. Ah, that's an annoying problem to have. Yeah, they're definitely 3.3 volt systems. It's the one annoying thing about NeoPixels is somebody decided that they had to run at 5 volts and made them that way. All right, I'll look into that some more. I think I'm gonna get this one, but yeah, it is an easier problem to solve. I mean, that's a pretty common problem, how to shift 3.3 volts to 5. But yeah, I need to figure out how to do that. I mean, the only thing that confuses me on it is that it just has to be fast because we're doing a really fast data rate, so I can't just throw a couple of big resistors on something and call it good. But with a pull up and a level shifter, you can do it. I've already got the breadboard out, so I guess that's not. I already have it here ready to go, so that's not that bad. Okay. All right, I think I'm going to call that an end to tonight's stream then. Thank you, Terrence, especially for your help. There's a lot of great insights there, and I'll have to recognize that. I'm trying to think of something to recognize because I'm desperately trying to get people to participate and help me figure things out. And so I don't want to to just be me sitting here the whole time. And so I'm trying to figure out a way to incentivize that. I don't know if recognizing people for just insights and things, would be cool, or what else I could do. But that was some good insight there. Now you got me thinking about the whole level shifting thing and all that. I think all that could work. I really want to know what this FlexIO module is because it sounds like almost a Yeah, no problem. It sounds almost like almost like FPGA fabric on a micro or something like that, which is really cool. All right, one quick reminder, maybe a few quick reminders if I think of more stuff to say. I will not be streaming on Sunday. Sunday streams are not happening anymore just because not much was going on Sundays, and I need more time to edit videos for YouTube. Another thing, the first video is up on the YouTube channel. It's just a cut down time lapse video of the Chapter 1 of the Millennium Falcon build. So check it out. And I'm really just using the Millennium Falcon build to hone my video editing skills. Obviously, they're not very good. You can see by how rough that first video is. But over time, I'm going to learn the software and get better. I'm using DaVinci Resolve, which is a pretty powerful software and probably the coolest free software I've ever stumbled across. And I think that's it. Also, if you have a project idea, please submit it, because I'm getting close to the end on this one. Once this SD card thing is figured out, we're basically done with this project for now, and I'm going to need something else to work on. So if you can think of anything, please submit a project request. All right, I will see you all later. Thank you for joining me. See you all Tuesday.